This section explains the Denoising Diffusion Implicit Model, DDIM, and code implementation. Let's first look at the DDIM overview. In DDIM, the main goal is to model the reverse diffusion process, which involves learning how to recover clean data, denoising from noisy data across multiple steps. The forward process gradually adds noise to an image, while the reverse process removes this noise step by step. Unlike DDPM, DDIM allows for faster sampling with fewer steps, providing the ability to generate high-quality samples in a more efficient manner. Forward process. The forward process introduces noise to the image. Given an image x0, the clean image, at time step t, we add Gaussian noise based on a noise schedule parameterized by beta t. The noisy version of the image at time step t is as follows. Reverse process. The reverse process aims to generate x0 from xt by gradually removing the noise at each time step. This reverse process is typically modeled as a denoising autoencoder. In DDIM, we model the reverse diffusion as an implicit process, which involves fewer sampling steps compared to the standard DDPM approach. The reverse process for DDIM is parameterized by a function that learns to predict the clean image x0 from the noisy image xt and time step t. The reverse process can be formulated as follows, where mu is the predicted mean, and sigma is the variance at time step t-1. DDIM introduces a key difference in how we sample from the reverse process, which is where the implicit aspect comes in. Sampling process. In DDPM, each step of the reverse process is conditioned on the previous step's noisy image. However, DDIM modifies this process to be implicit by adding a deterministic path to the reverse process. In DDIM, the reverse process uses both the predicted clean image x0 and epsilon noise to generate the next image at time step t-1. The sampling equation for DDIM becomes as follows. The noise sigma t comes into play when we add a stochastic component to the process. We add Gaussian noise scaled by sigma t to maintain the stochastic nature of the diffusion process. The term eta controls the stochasticity of the reverse process. When eta is 0, the reverse process is deterministic DDIM, and when eta is 1, the process is stochastic DDPM. Now we implement the DDIM code. UNet class. DDIM class. Testing the DDIM.